Okay, so we've got the final keynote presentation of the afternoon. It's a double team of Frank and Nick, and I think I'm led to believe it's Nick, then Frank, then Nick. So Nick is an Auckland-based structural engineer and principal at CompuSoft Engineering. Nick is actively involved in research, including the ATC 145 and recast floor projects that he is presenting on at the conference, and in continuing efforts to improve seismic assessment guidance for concrete structures. He's also the current Vice President of CSOC. And just to introduce Frank at the same time, Frank is a PhD candidate at the University of Auckland. His research focus is on the performance and retrofit of Hollowcore floors as part of the recast project. Frank is the lead author of the updated Hollowcore worked example and is involved in various industry-related projects.
Thanks, Jason. So Frank and I will try to keep you for as long as necessary, but no longer than required, and talk through where the recast floors project is up to that many of you will have seen mentioned in various forums over the last few years. Sticky control. So the recast floors project, very briefly, is a rather large collaborative research project that was set up roughly 3 years ago now as a collaboration between brands and the Universities of Auckland and Canterbury, plus a few of us hangers-on, and it's got many pretty cool features and obviously focused on retrofit of precast floors, but that necessitates understanding more about the floors as well. And what's really cool about the project is it's probably one of the most tight collaborations between the two universities that I'm aware of, and without going into the detail of the diagram on screen, I think the key point here is that the red items are things that have been run from or led by primarily University of Canterbury people, and the blue ones, University of Auckland people. But where it gets unique is that Frank, for instance, is enrolled as an Auckland student, but has spent months and months using Canterbury facilities and vice versa. So it's really taking advantage of the country's resources. As well as being involved in the research, brands have to be acknowledged as providing the majority of funding or direct funding for the project through the building levy. And then there's other large contributions from organisations like the Quake Centre, EQC, QuakeCore, and the Concrete New Zealand Learned Society. So obviously large research can't happen without a fair amount of funding being available. And it's also got a very large team of people involved, something like 9 students providing the engine room for the project, and then large numbers of technicians and academic researchers, and as was mentioned on the previous slide, good crossover back into industry, obviously with a number of us being directly involved, and then a fairly active oversight group that we consult as time goes on. Important points are reached to try and sanity check what's being done and make sure it's useful. The ultimate outcome of the project is really a target of developing thorough retrofit guidance for precast concrete floors. Obviously there's a strong focus on Hollowcore because of all the known problems with those floors, but we are going to be looking to cover off the other flooring types as well, so double Ts in particular, and to a lesser extent maybe flat slabs and ribbon infill will be covered as well. And that's really to fill in what's quite a massive gap in our knowledge or our available guidance at the moment. We're really the only information at any real level of detail about how to retrofit precast floors dates right back to the PCFOG report which was released in draft and then never finalised somewhere around 2009 from memory. And we'll come back to this guidance later on, but for those who haven't come across it, I think the links or the references in the paper itself, but it's pretty easy to find online still, and it's still got some pretty useful but quite high level commentary on what to do with precast Hollowcore floors at least, which needs some update, needs to be made more specific, but it's stood the test of time so far. I'm going to hand over to Frank shortly to take us through the guts of the presentation, and Frank's going to be talking extensively about what we've been referring to as the big frame test that was recently demolished down at Canterbury, after being tested a couple of times. And many of you will recall from conferences past other similar tests. And you might be thinking it's pretty expensive exercise to put 6 columns and a section of floor into a lab and however many jacks and technicians to run it all and so forth. So why does it need doing again? And unfortunately, I guess it ties into Rick's presentation this morning and other talks through the day, that the more you look, the more you find, basically. And so along with a couple of earthquakes, the progress of research over the years has just revealed more and more things that need looking at. And so the large frame was really the genesis of the recast project, or a thought from an early stage. But this one does have some quite different aims to those that have come in the past. So looking for different things and in different configurations. And so just to round things out before I hand over to Frank, the presentation and Hollowcore floors can be a wee bit jargon heavy. So a lot of you will be pretty familiar with some of this terminology, but for those who aren't, we'll be using a lot of 3-letter acronyms: loss of seating, negative moment failure, positive moment failure. And then a fairly key one that comes up through the talk is the concept of alpha and beta units. So alpha units, shaded red here, being the ones that run right parallel to an adjacent beam. And then beta units being ones that spring from essentially the plastic hinge regions at intermediate columns. So with that, I'll click through and hand over to Frank.
Yeah, as Nick said, I was involved in the big frame test, and in fact we did 2 of those big frame tests to make the most out of it. And my section is going to be focusing on the second big frame test, and I've put kind of the top view here with the alpha and beta units indicated. And so in this big frame, that is basically a big testing rig for Hollowcore floors, we had 200 millimeter deep Hollowcore floors and a variety of the typical 1980s Hollowcore floor details. And it's worth pointing out that we had negative moment failure critical detailing in this test. And on the top right, you can see this big test rig we had, and we were able with 14 actuators to actually load this frame bidirectional. But we actually didn't test only this bare frame. It was retrofitted, and we put into this frame 2 new developed retrofits, and that was a cable catch system where we had wire rope running parallel underneath the units, and then the second retrofit was the Strongback system with cantilever catches, looking something like this. So we basically had those UB sections underneath the unit, anchored with screw anchors into the unit, and then simply seated on a seating angle at the support indicated in red. And so we had 3 of those Strongbacks per unit because it was critical for shear to grab those 3 webs there. But really, you can be a bit more flexible if you design those retrofits. So you could, for example, use 2 sections and grab 4 webs or something like that. So how do those Strongbacks work? So here you can see kind of the typical negative moment failure, and I faded out the part that essentially gets useless after that negative moment failure occurs. And with this compression tension force couple you see there, the forces from the floor can be transferred into the Strongback section and then back to the seating angle and safely into the rest of the structure. So those Strongbacks not only help with negative moment failure, which is quite straightforward, but also with the positive moment failure, which is quite controversial, and it's insensitive as to where this crack is going to form. So this is the Strongbacks before the test installed in the big frame, and you might notice, hey, there's one that is different, and that is That is just a different variation where we had a single strongback, and then we had outriggers to grab 3 reps and get that shear capacity out of those 3 reps. Then the cable catch system that we installed in the big frame looked something like this in the elevation. So you had wire rope running parallel and underneath the units in the ceiling space, and then those diverters about 1 meter away from the support. And then, yeah, those were anchored back through stiffeners at the angles back into the beam. This is what it looked like installed in the big frame. And you might notice that these cables are actually slack. And that is to accommodate the beam elongation. When your plastic hinges starts cracking, your frame elongates, and you don't want to have the cables and the diverters popping up the floor, which could actually lead to other failure modes. So how did we load this frame? This is based on work from our colleagues at the University of Canterbury, Giovanni De Francesco and Tim Sullivan. They developed a building model, kind of a typical 1980s Hollowcore floor building, and subjected it to a pulse-type motion from the 1994 Northridge earthquake. And we got this response from this model when we subjected it to the earthquake. And worth noting is that we get that big pulse at the very start, up to 2%, which is quite large drifts for Hollowcore floors. And then 1%, and that was parallel to the units. And then we simplified it to 2 pulses to 1% in the transverse direction. After that, we continue with the progressively increasing drift cycles, but in an elliptical fashion, where we had a predominant direction parallel to the units. So what kind of damage did we see? And it's important to look at the damage to see how well our retrofits actually performed. And so we've illustrated it with plotting the damage we saw on the vertical axis, and then on the horizontal axis, the previous peak drifts. And at the top right, you can see we will indicate where exactly that damage was observed. That's our damage. So at the very start, at 0.5%, very, very early, we had web cracking. But maybe at the last row, it's really, really hard to see, so I highlighted it. So yeah, it's pretty tricky to see when you poke your cameras up into the cells. And yeah, then at 3/4 of a drift, 3/4% of drift, we had positive moment cracking away from the support, and you see those seating angles, so it's beyond the seating angle. And then at 1%, we had quite significant web cracking, and you see at the top it's quite a few ends of the floors that had that web cracking, and it's a decent size crack. And then at 2%, essentially all the floors had web cracking. And you see kind of the diagonal, quite shallow web crack in those floors, and I'm going to come back to that later on. Yeah, and something that we found is at residual, it's really, really hard to see those cracks because they're close up. So this picture was taken at 3.5%, and you see the strand is not even bonded anymore. And so all the retrofits at this stage supported the floor. And so we couldn't really say at what point this floor would have dropped throughout the test because we had those retrofits. So let me talk about the performance of those retrofits a bit more. So the Strongbacks actually did really, really well, and we had a piece of concrete, 20 kg, falling out of the side of the floor, and so the interior of the floor was exposed. And there you can see this big negative moment failure crack, and the Strongback perfectly supporting it. So we can recommend the Strongbacks. They performed really, really well. What about the cable catches? So this picture was taken just before the test, and this was after the test. And it's kind of a nice simulation there. You see how the cables actually tighten on the right-hand side, and how the floor drops onto the cables. And so that is one of the concerns with the cable catches, because they need to drop. So how does it influence the diaphragm performance? And then during the installation, we also experienced that it's quite complex to install those cables. So there are a few tricky things about the cables. So yeah, they kept the floor up. They prevented the floor from falling down. But yeah, it's probably not the best retrofit. And we not only looked at the new retrofits, or we not only had observations regarding new retrofits, but also what about seating angles? What about having only seating angles? And some of the damage we have seen was quite concerning because, as I've shown before, those cracks away from the support happen beyond the seating angle. So is the seating angle still effective for positive moment failure? Not really. And then we get those really, really shallow web cracks. And once the floor drops onto the seating angle, you get that secondary cracking. So there's basically not much support, no reliable load path anymore for this kind of failure. So Nick is going to take over, and he's going to come back to this and what it means for our retrofits.
Great, thanks, Frank. So the question, Frank's obviously talked through what was seen in the test and given pretty clear understanding that the tests provided a lot of good information about the retrofits used. The question, I guess, that comes up is, does the test change our understanding of how the floors perform absent the retrofit? And to some extent, as Frank's alluded to, yes, but there's also a lot of confirmation of what we've already known and what's been out there for a long time. So it's been pretty clearly documented for basically 20 years now that hollowcores are susceptible to damage, and quite concerning damage, from very, very small drifts. And by 2010, that was pretty clearly written down in the Purple Book, and so that shouldn't be too new or shocking. We've known about positive moment failure for a long time. It's been discussed, but the interesting thing is, talking to those involved at the time, it's always been conceptualised more as a 45-degree failure plane based on what had been observed in various tests in different configurations. The existence of shallow cracks through Hollowcore units has been known for quite some time as well. And so they've been a concern. They've been associated with negative moment failure. And that's really why for negative moment failure there's been so much distrust of how you can retrofit it, because the failure plane is so devastating to the integrity of the floor that you're not left with a lot to rely upon. Where the testing has given us new understanding, as Frank said, is that positive moment failure can quite easily be associated with very shallow angle cracking, and we'll come back to what that means. But that is quite a significant new bit of understanding that's arisen in the recent past. So going back to the idea of retrofit guidance, between the large frame tests and various other smaller testing over the last couple of years, there's been a lot of advance in what we understand about how effective different retrofits are for Hollowcore floors, and to a lesser extent for other types of precast floors. And the job now is really for us to pull all that together and collate it into a usable form for the industry. And that's what is being targeted over the next, the remainder of the project over the next 6 to 8 months, I guess, with the aim of getting things out as quickly as possible, but obviously with a concern about getting it out so fast that don't cross the T's and dot the I's. We want to make sure that we've got everything right so that we're not chopping and changing on things. And in the paper, we've gone through and put commentary on each of the various methods that are discussed in the PCFOG report. And as I said at the start, most of what the PCFOG report is broadly correct for these, and so there's items that work quite well or described as probably working pretty well in the PCFOG report, and they've now been more or less verified through testing, or there's no reason to think that the understanding changes. There's other things that the PCFOG report says basically aren't going to work. And again, there's really not been any change of understanding on that would suggest that we have a different opinion now. The ones that are probably most interesting or require the most discussion are a couple of items where an approach works within limitations or within a certain scope. And so I guess coming back to another theme from the conference of understanding what you're trying to achieve and the limitations of what you've got to achieve it with. And so I'll come back to angle retrofits in particular. As I said, various testing has shown that different retrofits are effective as they were anticipated to be. And so the idea of post-installed starter bars has been validated in small unit tests. And I think Frank will confirm they were in one of the large frames as well, right? Yeah. And so it's, fundamentally it's an approach that makes sense from an engineering perspective, and so it's satisfying that it works as expected. There'll be limitations if the diagram here tries to convey the fact that you have to have enough overlap between the existing starter bars and the post-installed bars to effectively lap onto one another. And so there may be situations where that becomes tricky, but that will become clear in the next few months as we elaborate on that aspect of things. Supplementary transverse reinforcement also appears to be a pretty effective technique. There's obviously always going to be discussion about what products work and what ones won't, and we can't test everything at this stage. The interesting thing, some of you may have picked up that Frank talked about using screw anchors in the large frame test and got really quite outstanding performance from those. The driver for using those was discussions with the industry groups suggesting that if you could develop retrofits that only required one side of a floor to be accessed, then that could be desirable in certain circumstances. So that was the driver for the screw anchors. Obviously, in a lot of scenarios, if you had access top and bottom, plenty of us would say, well, it's more obviously secure to bolt right through and have a positive connection onto the top. But, reassuring that there are options available there. One thing that we've not tested, and it's because past evidence suggests or supports theory that would say that it's not a reliable way of improving performance, is the idea of infilling cores. It seems to come up reasonably often as a suggestion, but the fundamental problem is that the insides of cores of Hollowcore units are pretty dusty. They're fairly smooth concrete often, but with a layer of dirt or whatever and uncertain debris in there. And so where a cold joint is not really a great tension load path, well, I guess concrete in general is not a great load path in the first place when you're subjected to tension. A cold joint's worse, and then you can probably put a reasonable argument that a cold joint inside a Hollowcore core is right at the bad end of cold joints. And so aside from not providing a reliable increase of strength, there's pretty compelling evidence that these could worsen performance too. So we really wouldn't recommend pursuing that sort of approach. Now coming to I guess problem child's not quite the right word, but an area where understanding has advanced quite a lot in a reasonably short space of time and not necessarily in a comfortable way. For a long period of time, people have been retrofitting deficient seating with extensions. And it's an obvious thing. If you've got a beam that can fall off a ledge, what do? You make the ledge longer. And so supplementary support remains an obvious and suitable solution for that aspect of performance. So if you've got a building with a 30mm seat, no other problems, then go for your life. Well-designed seating angles are probably going to be a good solution. What's become apparent from the recent testing and understanding of the angles that positive moment failure cracks can occur at is that angle retrofits are probably not sufficient to address a positive moment failure situation. Some instances they'd work fine. If you've got the nice steep failure plane, then they might be all good. But the trouble is there's a lot of uncertainty about the positive moment failure, both in terms of the inclination of the crack, and there's no obvious explanation at the moment of why some units crack on a steeper angle than others, so you can't exclude the shallow crack based on current knowledge. And then there's also a more long-standing question mark about where the crack actually forms. And Frank's testing on the large frame, or the large frame test down at Canterbury, a lot of the positive moment cracks formed a distance out into the span. Whether that was influenced by the units being cut out around columns may be the case, but that's pretty common in real buildings too. And then there's the remaining or the residual questions from observations after the Kaikoura earthquake, where positive moment cracks were found much further out into the span. So the concern, I guess, is if you have this shallow crack, you've got a very thin nib of concrete trying to sit onto an angle. And if you try and put an 8-metre span of floor landing onto that little nib with no real reinforcement to speak of, what's its capacity? We just don't know. It's probably not enough, and it's certainly not something that we're happy to rely on. The question obviously comes up, what about all the buildings where there are existing seating angles that have been installed and potentially installed quite recently? And the answer there really depends on what the situation is. If you've got a building where loss of seating is the concern, this is taken from the example that was in the CSOC journal a couple of issues ago, the floor might experience a loss of seating failure at 1.2% drift, then the seating angle will remain sufficient to take you past that drift, and it'll provide the support of the floor at that point, or to that point. So we've got a big angle in there now. The next failure in that example that kicks in is positive moment failure. And so what we're saying now is that we're not comfortable with the angle being able to address that failure. So at that point, the building would be limited to that sort of drift level, and you'd need to either be happy with that drift level or look at some other form of retrofit. And there are thoughts floating around that it may be possible to retrofit the retrofit in that situation, so don't throw the baby out with the bathwater, and if you've got some nicely installed angles, then the ideal thing would be to be able to take advantage of those still, and then maybe reinforce the unit with some of these screw anchors and some PFCs or something similar like that to basically provide retrofit shear reinforcement across that critical zone, hold the potential positive moment crack closed, and produce a more reliable end to the unit. We have to emphasise that is really, really under development. It's slightly more than an idea sketched on a piece of paper at the moment. Logic says that it should work, but it needs a lot of validation before you should go rushing off to start putting it in a building. We don't want to be heading down Rick's path of adopting solutions before we're confident that they're actually going to do the job for us. And getting towards the end of things, I guess what it all comes down to, the more we've talked through this as a project team and with the broader group who we're engaging with, is that from an engineering perspective, we really have come to the conclusion that Strongbacks have to be seen as the preferred retrofit technique for Hollowcore floors. In my mind, the clearest way of putting it is that these provide the best chance and a very realistic likelihood of taking your floor back to what you really would have hoped it was in the first place. So you're replacing a fairly brittle, unpredictable load path at the ends of these units with something that's much more robust and ductile. You're giving a load path that you can actually engineer and take the forces where they need to go. And I think a really key thing as well, Frank talked about the cable catch system causing the floors to drop, and it was quite apparent walking around on that test specimen after the conclusion of testing that one side of the floor was really quite fun. You could bounce around on it almost like a trampoline, The side with the retrofit, the Strongback, despite the horrendous condition on the underside, you really couldn't see any drop or disruption to the floor on the top surface. And so where that's going, I guess, is that they both provided pretty good life safety performance, but one of them, the Strongbacks, will give a much better performance in a smaller earthquake. And so you may, if you get a half code level earthquake, you'll see some damage in the floor, but it may not be enough to actually cause you worry about it. As Frank said, it may be possible that Strongbacks can be further refined, 2 versus 3 and different configurations to fit around things, and that's all in the works at the moment. So rounding things out, there is some good guidance in the PCFOG chapter, but it's too brief and not specific enough. We're working on an update for that, and we'll get it to you as soon as we can. We know that there's a lot of desire to have that information. The focus of it will be on various flooring types, but we've obviously a strong emphasis on Hollowcore retrofit. And in that scenario, just restating, we really see Strongbacks as the preferred structural option. They're going to give you the floor that you want and give building owners a resilient structure that will be closer to what they should have had in the first place. And with that, I will thank you all for your attention, and I'm sure that we acknowledge our project sponsors again and the whole team who've put in countless hours into making this all happen, and we'll be no doubt happy to answer any questions.
Hi Nick, you mentioned that you observed that the crack under positive moment failure starts away from the support. For argument's sake, if you keep increasing the angle, or the retrofit angle, would it keep moving forward, theoretically?
I'm happy for Frank to jump in here. I don't think that we had an inkling that the location of the crack was really driven by the angle. It sort of happened to coincide with it, and maybe once it was forming away from the support, it tracked to the angle for whatever reason. But I think the driver was more that the units were notched around a column, and so that introduces stress raises and unusual deformations at that point that then, for whatever reason, caused the crack to track across. The interesting thing, I guess, was that it wasn't just the notched unit where it happened, it then tracked to the next unit. So there was some sort of overall behaviour, but apparently influenced or starting from the notch in the units.
Thank you. That was very encouraging. Very encouraging. We're from Wellington, and we've got a problem down there. I think it's 110 buildings or whatever, lots of them. Clients desperate for a fix. So, Nick, is this bankable? That's my first question.
Bankable in the sense that we're going to make ourselves rich from it?
Bankable in going to the local authority to say, we want a building consent, please, to strengthen the floors using this method.
It should be, yep. It's, basically the engineering involved in the Strongback is, in a new design sense, 3101 and 3404, other than the screw fixings being a bit novel. And as I say, you could address that by taking it right through the floor. You're actually able to work within the bounds of normal engineering standards. So there shouldn't be any reason why it's not consentable. And as far as we have got to, it appears that it will address all the known failure modes for Hollowcore floors, basically.
Well, that's the second thing. I was quite intrigued. You showed web cracking there, which a couple of years ago was a total no-no. We were told that if the web cracking was there, you had to replace the units. Now, it appears that that's not the problem, just from the way it came across. So is web cracking sort of not such a bogey after all?
Web cracking in the, once you've got the Strongbacks there?
The cracking along the middle of the webs running horizontal. They emanate at the support, and they send
up where they emanated from the support in the test. The interesting thing and the reassuring thing was that the screw anchors obviously pre-compressed the web slightly, and so they really effectively clamped that crack and actually stopped it propagating further along, I'd have to hand over to Frank to discuss alpha unit performance and what the situation was there, but there were different retrofits installed under the alpha units to address the various behaviours there that can arise. So certainly web cracking is still a potentially very serious and arguably, borderline catastrophic problem, but the Strongback seems to be effective in suppressing it from extending to a point where it becomes a concern.
Great. Still got a little bit more time. Oh, right behind you. You guys making it right behind you. There you go. You don't even have to throw it. Just pass it. Yeah.
And Nick, Frank, thanks for the presentation, and thanks for advancing the understanding of the problem. I was just interested that we're a room full of structural engineers, but if we had a few building services engineers in the room, I'd probably start thinking, what consideration have we given to the practicality in the field in terms of installing these sorts of solutions? Yeah,
I mean, it's certainly, you'll be relieved to know you're not the first person who's raised that concern, that depending on the scenario and the building you're looking at, there could be all sorts of things that get in the way of that particular configuration of Strongback. I mean, we've probably all seen buildings where there may not even actually be enough ceiling cavity in the first place to fit that sort of thing. There are alternative ways you can install those as well. We, for an insurance situation, conceptualised slotting them up into the depth of the floor, and from a gravity perspective that worked pretty well. Needs a bit more thinking through to get consensus view on whether the cutting involved is problematic. So there are ways around it, but at the same time, it's obviously, if the services are right there, then it's going to be hugely disruptive to have to go and install the things. That'll be a project by project consideration that needs thinking through and working out what's viable, I guess.
Okay, still got a little bit more. Oh my gosh, the questions are coming faster as we go. Okay.
Should get Frank something.
Yeah, Frank, okay. You ready for a question?
That PCFOG detail, which you said doesn't work that well, where they have the ends of the cells kind of dammed in and filled with concrete, that looks substantially similar to the kind of 3101 current detail in the appendix or in the commentary, but I guess the one in the commentary has reinforcing, but doesn't address the cold joints in the cells. Have we seen any issues with, I guess, the current 3101 detail on that basis?
Very good question, and I'd almost say it's got two questions in there. So the first one, I guess, there is some similarity to the 3101 detail, and I guess the difference there is that the 3101 detail is conceived in a situation where the other reinforcement detailing is set up so that negative moment failure and positive moment failure should be suppressed in the first place. And so it's really there as a backup, loss of support thing to provide a fail-safe. And in terms of have problems been seen with 3101 detailing? Not in the testing, because it wasn't in the testing, because the testing focused on the real problem buildings, the older situations. In a broader sense, there are concerns about the detailing in 3101, both in the sense of whether it covers all of what's now known, and in particular in the sense that buildings with that compliant detailing still suffered some pretty serious Hollowcore damage during the Kaikoura earthquake. So I would think long and hard before specifying Hollowcore in a new building situation, basically.
Okay, well, I'm sorry I'm going to close out the questioning there. I realise there was more questions to come, and this obviously is a massive issue for the industry. Could I ask you all just to thank our speakers one last time, please?